Okay, so good morning, dear ladies and gentlemen. My name is Ivan Kolesnikov. I'm the reporter of Team Russia, and now I'll be presenting problem metallic forest. So the problem statement tells us that during the electrolysis of aqueous solutions of metal salts, fractal-like dendrites can begin to grow on the electrodes, and we should determine how the shape and fractal dimension depends on the relevant parameters. Now set up. So here's a brief overview of the report, and we're starting with the introduction. The introduction is presented with my experimental step, which consists of a piece of glass, which is covered with two pieces of silver foil with a thickness of about 20 microns. And in between, there is aqueous solution of silver nitrate. Then it is again covered in glass, and the resultant sandwich you can see on the left. Then, using a voltmeter and ampermeter, it is plugged into a power supply in order to control current and the voltage. And it is placed into the microscope with a camera attached to it, such that we can take pictures and make videos from our laptop. Let's firstly consider what is dendrite. So, because we have an aqueous solution of silver nitrate, it dissolves into silver cations and nitrate anions. And because of diffusion and external electric field, it migrates and diffuses into the cathode here, and here appears some surface reaction, and these ions deposit, creating our dendrite. So, which shape characteristics we may introduce? Well, obviously, maybe a surface area or average height, but there is a huge problem that it strongly depends on the section we're taking into account, like look on the right. Maybe we should consider average branch size, but once again, it's quite hard to determine what is an actual branch, how small should it be. So we come to the fractal dimension, which was asked in the problem statement. What is this? So if we take a binary image of our dendrite, we can apply a fractal dimension definition by Minkowski, which is a limit of the amount of cells covering our set to the inverse size of this cell. So if we keep making our cells smaller and smaller, we can make the plot on the right, which is the dependence of the amount of cells covering our dendrite to its size. So there are some regions, but we're interested only on the one which the size of which is comparable to the smallest branches, which gives us more information about the fractal structure of our dendrite. So coming to the theoretical descriptions, we use migration. We consider diffusion equation. So we take an assumption that the rate of deposition is much slower than the mass transfer rate, such that the time derivative of the concentration is 0. And to solve for the electric field, we use a Laplace equation. Here you can see the results of simulation, which will be described later. And you can see that pure diffusion trees are much less denser than the pure migration trees. And the ratio between the migration and diffusion will determine the characteristics of our dendrite. But why do we have a dendrite structure and not the single block of silver in our case? So if you consider just the pure diffusion case, we can see that it is described with some kind of Laplace equation. So the gradient of concentration is larger near sharp edges. So they will grow faster. And another fact we know about Laplace equation is that there appears some screening. So if there is a huge dendrite covering some area, the probability of the ion to deposit inside this cavity will be very small because it can't penetrate this barrier. So here you can see on the video how the dendrite grows, and you can see that as we described earlier, we can see exactly what happens. So sharp edges grow faster, and areas which are covered by the dendrite grow much slower. So generalizing this, there are three main reasons. So firstly, it's electric field distribution, so that electric field is much larger near sharp edges, and the random walks that create such structure. So if, for example, we consider that our dendrite grows like a single rod on the top, so the probability of the particle coming from the top to deposit on its side will grow instead of the probability of top deposition. Now, considering the surface reaction, which happens when the ion touches the cathode. So there appears some chemical reaction, but applying some transformations, we can generalize it such that when a particle collides with a cathode or another dendrite branch, there appears some probability of the deposition, and otherwise it will continue to move. So based on these concepts described earlier, we can present a numerical simulation. Using a Monte Carlo algorithm, we can solve the equation given above. So dividing our lattice, our solution into cells, we can seed it with particles, then randomly move it according to the algorithm presented before. And in case of deposition, we can add this particle to the dendrite. Also, there appears surface relaxation, which is just process of energy minimizing. So the more neighbors you have, the less your energy is. So here are the results of the simulation for different cell sizes. We can clearly see that as we decrease the cell size, the fractal dimension approaches some specific value. And the interesting fact, and one of the main results we obtained from the simulation, is that fractal dimension doesn't depend on the cell size and time. It depends only on the set of given parameters, of course, from some critical value in case of cell size. So our model has one free parameter, which is used for approximation. It's the reaction probability. It's very hard to determine from some chemically. So what we did is we conducted some calibration experiments. So the plot on the left is the dependence of fractal dimension to the reaction probability in the numerical experiment of two parallel foil sheets. So conducting the same experiment, but in real life, we can, from the photo, determine the fractal dimension, solve the inverse problem, and find the reaction probability, which in our case is about 15%. Knowing this reaction probability, we can start to compare the numerical simulation to our experiment. For example, the dependence of the fractal dimension to the applied voltage. You can see that here, as we increase voltage, the fractal dimension approaches some value. And if you remember, it's because the ratio of the diffusion term to the migration term is shifted into the migration term. But the area of applicability of our theory and experiment is limited, because if the voltage is too high, they will start an excessive electrolysis, and if it's too low, the anode will dissolve because there is not much silver. As it was asked in the problem statement, we can control fractal dimension. For example, here you can see the plot of the fractal dimension depending on the concentration of the silver ions and the applied voltage. So to solve the inverse problem, for example, let's say I want a dendrite with a fractal dimension of 1.6. So firstly, I calculate this plot and then just solve the inverse problem and find the specific voltage I need to grow this dendrite. So moving to the conclusions, I want to say that this dendrite-like structures are because of deposition of silver ions, because of the migration and diffusion, and the structure of the Laplace equation. Here are my references, and thank you for attention.
Thank you.
So hello everyone, my name is Felipe Mazzi from the Brazilian team, and I'll be opposing problem number 12, metallic force, as presented by the Russian team. So first of all, thank you very much for your presentation. It's important to remind ourselves that the problem statement asks, how can the dendrite shape and fractal dimensions be controlled by choice and variation of the set of parameters? So to give a quick overview of the presentation, we found that the Russian team built a great experimental setup. There was a very good video quality, and it shows it was very easy to see the phenomenon. Their simulations were presented clearly, and we were very satisfied with the overall clarity of the presentation. The fractal structure was discussed at reasonable length, and they attempted to define it with care. They made a short overview of theoretical principles, and most concepts they provided very nice visualizations for most of the concepts they discussed. So it was very nice to watch this part of the presentation. There were a few points in which we were a bit uneasy. So first, in slide 20, since your most important conclusions, since your discussions about the dependence of the physical parameters such as temperature and voltage and the parameters of interest such as dimension and shape depend on the curves that you showed for the dependence of these variables, it was a bit worrying that your choice for a analytical function describing the relation between the two was somewhat arbitrary. I understand that you maybe search for the most intuitive solution, which provided a good fit, but it's important to ask ourselves where that particular expression comes from. So this is the first point. The second was that I understand that it is somewhat complicated to find a proper analytical dependency between, for instance, when you showed some parameter to quantify fractal shape and temperature. I was a bit lost in what do you believe the physical mechanism there is behind this correlation. So you made the numerical evaluation and it seemed to agree with your data, but it would be nice to discuss the actual physical mechanism. How does temperature change, for instance, the properties of the random walk and the probability of a collision occurring in the deposited fractal. We also a bit we'd like to have seen some other parameter changes, such as different salts and perhaps different, well, most importantly, different salts for now. So our points to discuss would be, to the physics fights that will follow now, would be the effect of temperature and voltage in the physical sense, and understand it in chemical terms also, because we believe it was presented mostly as a numerical result. We'd like to discuss the physical meaning of the fit, where the origin of the expression which you showed, f of x, in the slide that I questioned during the opponent's questions. Other types of particle movement besides random walk, which you included in your simulation, and the way you chose to define the shape of the fractal. I understand that you discussed it, but it wasn't yet clear to me how you decided on one definition rather than another one. So with that, I'll conclude my speech. I think the clock was started a bit later, but now I invite the reporter to the fight. Maybe we can begin with the discussion on just to follow the order that you chose in your presentation, discuss of the definition of shape and
okay,
dimension.
So ask your question.
Maybe I didn't understand your question then. Sorry, can you repeat it?
So that's your discussion. Can you start, please? Oh, I think there is some connection issue. Maybe. Okay, so.
Oh, sorry, I'm asking you to take your slide to the beginning of the presentation so we can discuss the definition.
Oh. Okay, sorry. So which one?
Around slide 10, maybe. When you decided on the definition of, yeah, right. So you decided it wasn't quite clear to me still why you decided to, did you need to divide this image into squares? What was your point?
Okay, so the fractal dimension definition by Minkowski is such a limit. So you take your set and you keep dividing it into smaller and smaller cells with a side length epsilon. And the limit of the ratio of the logarithm of the amount of cells which actually touches your set, in our case, it's the white part of the dendrite picture, to the logarithm of the size of the cell, that limit is in fact the fractal dimension. So by taking this, by dividing our picture into cells, we can that's a straightforward method to compute the fractal dimension.
No, okay, so thank you. That was mostly a clarification. But I think we should discuss maybe concerning the actual statement of the problem, because the main point was to describe how the shape in fractal can be controlled by variation of the set of parameters, right? So you presented a numerical comparison between the two, maybe one of your last graphs, around slide 25 or something like that. 25 maybe. At the end. Yeah, that's okay. 26. Yeah, you show the fractal dimension as a function of the reaction probability, right? So you have to ask yourself, how does temperature, for instance, change reaction probability? I think that was in terms of the actual physical mechanism.
Because the reaction probability is something that we introduce as a feed parameter, I can't actually tell how it depends. However, based on my small chemical experience, I believe it will increase, but slightly. In our experiment, the temperature was room temperature, and the single experiment may run up to half an hour. So the temperature fluctuations were negligible in our case. So I believe it was a constant parameter during our experiments.
Okay, sure. But do you expect, for instance, considering that you're modeling your collisions as being due to being results of a random walk, how do you expect temperature to affect this probability? If I increase it by a lot, for instance?
Because we find this reaction probability from the actual experiment in comparison with the numerical experiment. So it wasn't changed. But as I said, I believe it would increase, but in our case, we didn't observe such increase.
So so I don't see what your goal was then in fitting this function particularly, because if you're not trying to verify anything, I'm a little bit concerned that it's just you don't have an expectation, right? Okay.
So because this plot was obtained from the numerical simulation, there is no analytical solution for this dependence of fractal dimension on reaction probability. And because there is none, we are free to use, for example, linear interpolation between the points. However, the interesting thing we noticed during the processing of the data is that this plot is very well approximated with a function given above. So that is not necessary to use this kind of fit. You may use linear interpolation, but we found interesting that it follows such trend.
Okay, but for instance, in your conclusions, for instance, you said that higher applied voltage leads to denser growth, and that higher solution concentration also leads to denser growth, right? So I was especially concerned, for instance, when you talked about the higher voltage, that you didn't. Could you discuss the actual physical mechanism behind this correlation, right? Because you showed experimentally that there is such a correspondence.
Okay.
But I was missing an actual discussion. So is there no discussion on that?
So you're asking about physical, what the physical background behind the relation between diffusion and migration, and why the diffusion
because I was convinced
how much.
Yeah.
Okay. So if we take a look at some simulation result, for example, here, yes. So I believe this is because the In case of migration, we have an electric field which, like in this photo, leads our particle straight to the bottom, and the particle may, like, if you are trapped inside a small cavity, the probability of the particle to move downwards and to attach downwards to create a dense growth is higher, because in case of a pure random walk, you may just start to wandering around and hit the wall and block the passage of the other particles into this cavity. So generally, that's because electric field forces particles to go down. That's something like gravitational potential. I believe it may be interpreted like that. And
okay, I see. I think you could make a similar discussion on the second conclusion which you presented, which was about solution concentration. But maybe I think maybe there won't be enough time for this, because I think Anderson has a question. Sorry.
Yeah. Greetings. Thank you for the presentation. It was really nice explanation of the problem. I really liked it. So I would like to ask if you thought in change the salt you were making the groove. Use like copper, some copper salt or something like that.
We didn't, because we used silver because we found very thin silver foil, which was very nice for our experimental stuff, and we didn't find one for a copper. And another point of not using copper is because copper sulfide is strongly blue, and it strongly reduces observability of the dendrites.
Right.
That's not very
how
useful.
about the concentration of the
actually, we found out that concentration doesn't depend strongly. While the concentration is quite small, of course, it influences. However, when it is large, and it almost doesn't affect the conductivity, so it doesn't have much effect.
But you would have seen another kind of patterns, right? With different kinds of concentration, because you would have a lot more molecules interacting with this random walk and another kind of movement.
You're quite right, but where does our silver come from? Our anode starts dissolving. So when all the initial silver cations, which were dissolved in the solution, are deposited, all the silver starts coming from the anode. So as you can see, for example, on here, the anode starts dissolving. And that's why most of the ions come from the right, not from the solution itself. So after the ions are deposited, the ions come from the anode and not influence the shape. Like the concentration stops taking, we can stop taking concentration into account. Yes.
Thank you.
Okay, do you think you could maybe extend the discussion to include, for instance, the particular branching pattern of the fractal, or was that completely out of the picture?
You mean, can we grow absolutely the same tree as the simulation, or?
No, I mean different fractal, the branching pattern, right? Because you control the shape and dimensions, but I don't think shaping includes the branching pattern.
So the trick is that that's quite hard to mathematically determine what is different shape. As I mentioned here, the matrix of branching and the pattern is quite comprehensive. So we found that fractal dimension is most applicable in our case. But I'm pretty sure that there may be some quite complicated metrics which will describe the shape much more completely.
Okay, thank you. Thank you for a nice discussion. So now the reporter can make concluding remarks.
Okay, thanks to the Team Brazil for a really fruitful discussion. I liked it. There were very interesting questions raised. For example, the usage of the copper. I think that it's a further improvement. About the remarks which were raised during the report overview by the opponent. For example, he said that we didn't investigate the electrode shape. However, for example, you can see that we conducted the experiment with a triangular shape to see that the branching, the dendrite starts to grow faster on the near the sharp edges. And other experiments were conducted on the flat-to-flat pieces of foil. So partially, we considered the effect of electrode shape. So that's all. Thanks to the opponent for the discussion.
Okay. Thank you. And now the jury can ask their questions. Who would like to start? Yeah, okay.
I would like to start. So, question to the reporter. Did you investigate the problem in 3 dimensions?
No, we didn't, because firstly, while we were solving our numerical simulation, the vast majority of the computation time was taken by the solving of the Laplace equation in our grid. And if we shifted into the 3-dimensional, that's the complexity of the computation grows rapidly, and that would take very long time.
Thank you for answering my questions. And one more quickly to the opponent. You and your teammate spoke about using different salts, different metal salts. Is there a reason for why this would make the problem more interesting?
Oh, sorry. So yes, there's some reasons. One reason we could found in the literature is that if you try to change the salt you're using, you're changing the metal, of course, and changing the metal, you are changing some features like the latent heat. And if the latent heat is lower, you could have a more faster growing and some more other characteristics of the dendrite you're
Okay, I understand your point. Thank you. I think we should allow other jury members to ask questions.
May I ask?
Yes, please.
Yeah, I have a question to a reporter. Did you take into account change of electric field due to presence of these fractals or these structures?
Yes,
that
sure.
grow?
The dendrites and electrodes were considered as perfectly conductive. So the electric field on its boundary was the potential on the boundary was considered during the computation of Laplace equation.
Okay, thanks. Probably for now that's it.
Any more questions?
I would like to ask a question to the reporter. There are various definition of a fractal dimension in literature, I mean, and you have chosen only one of them. Like, why didn't you choose another one? And maybe just a follow-up question to both the presenter and reporter. You would discuss this problem of the concentration, and for instance, on your slide 6, when you have the picture of your fractal, it seems like the concentration is affecting the fractal pattern, right? And like now again to the question about the dimension of the fractal, there is a notion of multi-fractal dimensions where the scaling of the pattern varies in different parts of the space. And you can see that on the left of this picture, the fractal dimension will be different from the right of the picture, right? So yeah, whoever wants to answer first.
Okay, firstly, about your question about different definitions of fractal dimension, we chose fractal dimension by Minkowski because it's, I suppose, the most simple and most suitable for our applications. And I didn't know that there are multiple definitions. Well, I know that for some crazy topologies, there may be some, but I didn't consider it.
I mean, you basically used boxes to like simplify
Yes.
boxes, but you can do also with lines. For instance, it's
yes. Some algorithms utilize spheres and so on, but because we have pixels, the boxes are perfect. Okay, so what was the second question?
I would say for the opponent team, because you raised this question about the concentration, and at the end I didn't like understand what was the conclusion from your side. Do you agree with the reporter that the concentration do not affect the fractal dimension or the fractal pattern?
In general, no. I think as you raised it, maybe this picture is a good example of it, right? But we were mostly during the presentation. We were mostly concerned about their choice of how they decided to say that they both are related. But the short answer is yes. We believe that the concentration does affect fractal dimension, and we think that this is a nice demonstration of it.
Okay, more questions?
Clarifying question for reporter. Can you list what parameters did you change during your experiments?
Concentration, electric field, electrode shape. I believe that's pretty much all.
Thank you.
Maybe I'll ask a question as well. For these particles that are randomly distributed, did you try to somehow induce a larger or smaller number of them experimentally?
Yes, and that's presented on this plot. So we conducted 225 numerical experiments, and depending on the applied voltage and the concentration in our simulation, and this concentration basically represents the amount of initial seeding particles in our simulation, and that's how the fractal dimension depends on the set of these two parameters.
Okay, but experimentally, can you control the number of seeded particles?
I didn't get. Do you mean can we control concentration or what?
I don't know. What is your number of seeded particles in real life?
That's correlated with the concentration of the silver nitrate.
Okay, what is the correlation?
Well, that's quite relative. I can't just say that. Well, we may interpret this as the volumetric ratio, something like this, but there's I can't name it.
So there is no exact dependence between the fraction of seeded particles and some physical quantity that you can measure.
Once again, please.
There is no direct dependence, exact dependence that you can formulate in terms of formula, or I don't know,
in terms
some coefficient.
I think there is. Well, that's so the n which is presented on this plot is the fraction of the seeding particles to the whole amount of particles in our simulation, or to the whole amount of cells. And by determining this ratio, it may be correlated with a experimental concentration with a volumetric shape, like.
Okay, I see your point. I see your point. So you think there is, but you did not determine it, or you did not show it, right?
Well, we found out that the fractal dimension doesn't depend on this concentration. So yes, I don't have the exact formula for a transition between the numerical simulation concentration and the real life one. However, we find out that it doesn't depend much on it doesn't influence much on the fractal dimension. So there is not much to
Isn't your simulation telling the opposite?
Sorry?
Isn't your simulation telling the opposite? That there is a dependence?
The dependence of the
fractal dimension on the fraction of seeded particles.
If we take a slice, there will be almost a straight line parallel to the concentration. Unfortunately, I don't have this one here, but there is some noise. However, it doesn't depend strongly on a
Okay, so the other axis is what?
Applied voltage.
Okay, so it's mostly dependent on voltage and not on the concentration. Okay, thank you.